Ready to go? Okay. Good afternoon, everybody, and welcome to the fifth session of the Spring's Education Policy Colloquium Series, sponsored by the Program on Education Policy and Governance. My name is Jim Pizer. I'm an academic visitor here at Kennedy School, and I'm the former Massachusetts Secretary of Education. It's a privilege and honor to work alongside Marty West and Paul Peterson here at Harvard in support of the Colloquium Series. After today, we've got 4 more sessions this spring running through the month of April on Thursdays at noon and mostly here at Taubman. Some of the upcoming topics we'll be talking about include chronic absenteeism, the effectiveness of preschool, the state of post-COVID academic recovery, and the full listing of those sessions and the speakers are on the PEPG website. So check it out. Our next session is this coming Thursday, or next Thursday, April 4th. When our speaker will be Anna Egalite, who's an associate professor at North Carolina State, and she'll be presenting her research findings on the impact of teacher diversity on student learning, specifically focusing on the matching of students with teachers of the same race or ethnicity and that effect on educational outcomes. So hopefully we'll be able to join us for that session and all the other ones. Today's session is about student assessment, and specifically the hidden value of state testing data for informing educational practice and predicting student outcomes. I think it's fair to say that state testing programs have always been a hot button issue, but they're especially controversial with regard to how the results are sometimes used to evaluate teacher effectiveness or to hold schools and districts accountable, or as a standard for student promotion or other benefits like college scholarships. And as you probably know, we're facing a potential ballot campaign here in Massachusetts on whether MCAS should continue to be used as part of the statewide graduation requirement, as it has been for the past 20 years. But more importantly, in the midst of all this controversy, there has been little discussion about how we could improve the usefulness of the mountain of data that is produced each year by these state testing programs. And thankfully, we have today's speaker, Jesse Bruhn, who will be presenting research findings on the potential for using item analysis from state assessments to provide more useful information about student learning and future success, than much more than just looking at overall scale scores or performance categories, which is the way most people use the information and what we pay most attention to. Jesse is the assistant professor for education and economics at Brown University and the Annenberg Institute. He got his PhD at Boston University and also taught math at Springfield Public Schools. And there is some math in the presentation, so apparently you know what you're talking about. After Jesse's comments, we should have ample opportunity for questions and answers and discussion. And we'll give priority to folks who are here in person, but we are live streaming online via Zoom. And so if we have folks who want to comment or ask questions, please put those into the chat and we'll try to get to you as well before we're done. The session is being recorded and will be posted on the PEPG website. So in effect, we're all on the record today. And with that, it's my privilege to turn the program over to Jesse Bruhn. Jesse, thank you.
Thank you very much for having me, Jim. Also, if possible, after this, would it be plagiarism if I stole your notes and put them directly into my introduction? Because that was very well put.
Hopefully I didn't steal any of your best lines, but yes, absolutely.
Thank you all so much for taking some time out of your day to be here with me. My name is Jesse Bruhn. I'm an assistant professor in the econ department at Brown University. This is joint work with Mike and Jens and Sendel, and the research project is called What's in a Question? Using item response data to uncover the hidden structure of student achievement. So, okay, that's right. Perfect. So I probably don't have to say this to folks in this room, but testing at this point in time is a major component of the education system in the United States and abroad. And I think it is arguably among the largest ongoing data collection efforts in existence. And it also comes at an enormous cost. We can quibble about kind of exact numbers of the monetary cost of administering and proctoring these exams, but by some estimates, in some districts, standardized test taking and prep can occupy as much as 18% of scarce instruction. Okay, so why are we collecting all this data? Well, rightly or wrongly, or for better or for worse, it is increasingly used to inform the kinds of high stakes decisions that we hope will improve the nature of the education system, whether it's the teachers we decide to hire, retain, promote, and fire, whether it's the students we deem worthy of college scholarships or deserving of extra support and services, or the types of educational interventions that we believe are promising enough to scale up in the hopes of generating system-wide improvements in performance, all of these things increasingly rely on tests. But the reality is that we don't actually use the tests themselves to make these decisions. Okay, no one has ever taken a stack of bubble sheets and handed them to a high school principal and said, good luck finding your most effective teachers. What we actually do, or what the state level standardized testing apparatus does, is it takes rich patterns of student performance, the actual answers they give to test items like these, and they run them through an aggregator that's going to reduce these rich patterns of student achievement down to a single number, a simple metric meant to embody everything that the test can inform us about student learning. Okay? And there's some statistics behind this. You know, typically in the US, a lot of times these are done with like IRT or MIRT models. Okay, I guess there's two equations in the talk. I tricked you. Typically runs through an equation that looks like this, spits out a number called an IRT theta that probably many of you are familiar with. At some level, some form of aggregation is unavoidable. I don't want to live in a world where we are actually handing bubble sheets to policymakers. And under some assumptions, the particular types of aggregation, and it's specifically the choice to reduce these rich patterns of performance down to a single summary metric, will be optimal for the types of decisions we're using them for. But the point of view we're taking in this paper is that we don't actually care necessarily about the statistical properties of the aggregator itself per se. What we actually care about are the way we use these summary metrics to inform and make these high stakes decisions. Okay, and ultimately it's an empirical question whether there is this extra information in the items and whether it can be repurposed to create a more just and equitable education system. Okay, and so let me just give you one more stylized example of kind of what we view as like the current paradigm of decision making. Okay, so like one way you could do this would be to take each individual item, and let's say you wanted to learn like which students were at risk of not graduating high school. You could try to directly understand the relationship between performance on these test items and high school graduation. Similarly, maybe for a different decision, you want to know which students are sort of on track for college. You could take the items and then try to directly learn about the relationship between what student performance looks like on the test and their likelihood of going to college. Okay, what the current model does, the current decision-making paradigm, is it effectively funnels all that information through a single dimension of learning that we're going to call ability. And then you can imagine if that single summary measure captured all the relevant information in the items, you could then use that to understand these long-run outcomes, and we'd be done. Okay, and so what we're going to try to understand is this model correct? Or are there other arrows missing from this diagram going from the items into these outcomes that could help us improve the education system? Okay, let me give you sort of 3 facts that we believe are true based on what we've done in the data here. And then I'm going to basically spend the rest of the talk just sort of elaborating on these 3 points. First, there is systematic variation in the items. Second, this extra information does improve our ability to predict who is on track to do well for these long-run outcomes. And 3, incorporating it has the potential to radically change how we make educational decisions. So just to preview a little bit more, even looking at 2 students with the same average ability, the types of items they're answering, correct or incorrect, can be systematically different. This suggests that even weak students have real areas of strength. Even teachers at the bottom of the distribution of summary performance metrics can have real strength. And similarly, that people doing strong on traditional measures can actually have real areas of weakness that the system could try to improve. Okay, and in total, we find that by choosing to reduce these patterns down to a single number, we lose something on the order of 70% of the predictable variation, the systematic variation in student performance that we can be otherwise leveraging in the education system. Okay, we're going to show you that this extra variation is actually closely connected to the long-run outcomes we care about. Incorporating it into models meant to predict who is on track for various outcomes suggests that we can improve our understanding of who's on track to graduate by 15 to 30%, who's on track to go to college by 8 to 10%, in your earnings 5 years post-college by as much as 45%. Okay, so this extra information, not only is there a lot of it, but it's important for the things we actually care about. And finally, we're going to show you that incorporating it changes how we make educational decisions. Simply put, depending on how we construct our measure of who constitutes a, for example, high or low performing teacher, we're going to get less than 50% agreement relative to more traditional metrics that are currently used in the education system today. Okay. So that's everything I'm going to try to tell you. Let me go into a little more detail about each of these claims I've made. Oh, before I do, let me tell you what data I'm using. Okay. We're using data from the Texas Education Research Center. We're going to observe the universe of students that attended K through 12 public education in Texas. Just to give you, oh, sorry. Oh, yeah, I got to point it down here. Why are we using this data in particular? Well, one, it is one of the few data sets we could obtain access to that actually shared with us the raw items that students answer on these tests. In a typical year in grades 3 through 8, which are the test taking grades, kids answer 45 or so items and get about 61% correct. The other thing that's a really nice feature of the Texas data in particular is that it's huge, which is going to be critical for leveraging some of the machine learning algorithms we're going to use to try to demonstrate some of these facts to you. So in total, in our test taking sample, we have about 4.5 million distinct students. When you then break that down by the number of items they answer over the course of their life cycle in Texas, we're going to have about 1.3 billion observations. So a rich, large data set that's ripe for some real modern machine learning techniques. The last reason we use the Texas data is that, unlike many educational data sets, this is linked to long-run outcomes. I actually don't have the summary stats here, but we also have wages as well. High school graduation, college attendance, wages.
Jesse, what years are you using for the test score data? And is it the old Texas test or the more recent one?
It's a mix of both. So there's some subtlety here that I'm glazing over, which is that we have teacher links through from 2016 to 2019. And then we have test score data. I need to double check the paper, but I think I can't remember if we started in like 2012 or 2011, around the time they make the switch, but I don't believe we're going back into the old test. I believe it's all. I can double check that though. I'm a little. Okay. Now that I've given you a sense of the data I'm working with, let me unpack this first claim. Okay. So how are we going to use the data to check how much additional useful information is in the items? Well, this simple model of decision making here suggests that if you know a student's average ability, there should be nothing left in the information that's useful at all. The rest of student performance should just be pure noise. It should be random errors, people bubble in the wrong sheet, rather than something systematic about the way they're answering tests. That means if I construct an ability measure using these 3 test items, I should get the exact same ranking of students, the exact same understanding of where they stand in the distribution, as if I use these 3 items to construct their average measure of ability. So basically, up to random mistakes, student performance should be identical on every individual item of the test, every individual subset of the test, and that's the first claim we're gonna check in the data. Okay, so I was living in fear of not having a single equation in this talk because I knew there were going to be some economists here. So I promise this will be the only one. We're gonna test this by estimating 2 fixed effects models. The only thing I really want you to take away from this is that we are going to include question level fixed effects. This is going to account for the fact that some questions are more or less difficult than others. And the object of interest are basically going to be interactions between, for example, down here for the model for teachers, a teacher fixed effect and a question fixed effect. And a student fixed effect by category fixed effect. So these encompass this intuition that quantifying these measures for different subsets of the tests or different items should give us the same thing if there is no extra variation over and above question difficulty. Okay, so technical aside over. Let me show you what we would expect to see out of this exercise if the existing model of decision-making made sense, if it were sensible to reduce student achievement down to a single number. Okay, so what I'm going to show you now is for about 3,000 randomly selected teachers in 4th grade in Texas in the same year, their rank in the distribution of average performance. So this is using a teacher value-added model to try to quantify which teachers do a really good job of predicting test score growth. Each slice of this bar I'm showing you here represents one of those teachers, okay? The teachers at the top of this performance measure are up here in light blue. The teachers at the bottom of this performance measure are down here in dark red, okay? We're gonna fix that color, okay? Then what we're gonna do is we're gonna plot for each individual item how well they are predicted for students to grow on those items, okay, as opposed to on average. Now, if there really were only a single dimension of human learning, if there was one thing called ability that's being captured by this average performance measure, what would we expect to see? Well, we'd expect to see this ranking reproduced item by item by item, except for a little bit of mixing as a result of the fact that there's some sampling variation, that people are like making mistakes. There's a little bit of randomness to it, okay? So this is what we would expect to see. What do we actually observe in the data? Well, when I look at the first item on this test, we see an enormous amount of mixing, okay? There are teachers up here that if you just looked on average, you think we're at the top of the distribution that fall all the way down to the bottom of performance measured for this individual item. There are also teachers down here at the bottom that rocket all the way to the top. And it turns out that's not true of just 1, 2, or 3 items. It's true of the entire distribution, okay? So what does this mean for policy and practice? It means there are teachers and students with real areas of strength that we could build upon and leverage to make the system better. There's also teachers and students with real areas of weakness that we could identify and provide more informative feedback to improve. Can I, is anyone here, will you be offended if I curse?
We'll be okay.
You'll be okay? Okay.
We can edit anything.
You edit it out? I don't know, it's the Kennedy School. It's pretty fancy around here. Do you guys know this term, the McKinsey shit sandwich? Has anyone heard this before?
No.
Okay, it's a term from consulting. When you go give the bad news to the CEO, okay, when you deliver the bad news, you want to wrap it between 2 slices of bread. You want to give them two positive things to cushion the blow of the thing that's the bad news. I would liken the current way we use educational data to giving teachers, for example, a shit sandwich with no bread. Okay, we're telling them you're here at the bottom of this distribution of performance when the reality is they may have real areas of strength that would also be good to acknowledge and help them continue to grow. Yeah.
I'm thinking about, like, if you go back to the prior graph, that look, the one that, like, what we'd expect in a random noise, that looks like what I would expect if, like, I was giving a whole different test each time. Like, that looks like the measurement error I would expect at the test level. So I imagine a test that has like an internal consistency of 0.9 and it's based on 45 items. The reliability of a single item might be like 0.2 or 0.3. So when I see that next graph, I'm going, well, yeah, there's a huge amount of noise, but these are single items. So how should we think about the amount of noise we should expect?
Yeah, so basically the way you should think about it is for the individual items here, the kind of power, if you will, to detect the systematic variation is not based on one individual student. It's based on the number of students per class. And so to the extent that you expect the measurement error to matter there, the kind of effective N, if you will, is more on the order of like 17 to 23. Now that's not a ton. What we're actually doing here, though, is a little more subtle than those regressions I showed you earlier. We're adapting the jackknife empirical Bayes techniques that are used to estimate teacher value added and cut out this noise and these classroom shocks in average scores to the item level. So like our de facto power or reliability, if you will, is not really determined by the reliability of the items. And in practice, we're going to be able to get rid of most of that. We also, in the paper, and you'll see in a couple slides when I show you a table of results related to this, construct some formal statistical test statistics that literally incorporate the noise to try to reject the null that there's no rank swapping going on, and we can definitively reject. So if you're worried about noise, I promise you this is not noise. This is just like a nice visual benchmark for what we would expect to see. And I'm happy to tell you a little bit more detail about how we constructed the simulation later if you're interested. Okay. Let me keep going. Good question. In the longer hour-long version of this, where I get into all the guts of it, that would have all come out in the preceding slide. Oh, so that was for teachers. For students, we have a similar figure I want to show you. I just want to highlight we're a little more limited with students because we can't actually, each student only answers each question one time. So I cannot construct a similar figure because I only see whether they got it right or wrong, not how they would do if you gave them the same question many, many, many times. So what we do instead is use categories as kind of like a way of testing whether performance is similar on similar types of items. So I'm going to show you here are the actual the categories. Again, this is what we would this is where each of these 3,000 randomly selected students stands in kind of the average score on the test. This is what we would expect to see if there was only a single dimension of learning plus a little bit of measurement error, okay? But then when we go to the actual data, as with the teachers, we still see a substantial amount of mixing. Now, again, it's not quite as dramatic as it is for teachers. I think that is likely because the categorizations we have are not great, but it's still there. So I've just shown you kind of some what we think are quite striking visualizations suggesting that there's all this extra information in the items. Let me just try to put some numbers to it. And basically what we're going to do in this table is show you what share of the total amount of information in the test is lost by choosing to focus on a single summary measure rather than try to illuminate these richer patterns. And I'll start with teachers. And I'm showing you this, we're calling this information loss measure for each grade where we can estimate teacher value added in each year in the data, as well as a summary column that kind of averages across all year. And then for those of you who are more statistically inclined, this is a formal test statistic that rejects the no information gain. And I can tell you more about how we build it later if you're interested. But the big picture is we are losing most of what teachers do. In virtually every grade and year, we're seeing at least 60% of the growth in student test performance gone when we choose to move from items into a single aggregate measure. And as much as 75%. For students, again, the numbers are not quite as dramatic, but if you told me that I was throwing away 9 to 20% of what we know about how students do on tests, I would tell you that's crazy and that we should probably be trying to use that information. So the short answer is we think we're losing a lot. Okay. Let me go on to claim number 2. Okay. So it is one thing to show the existence of this extra information. It is at least theoretically possible, though, that this extra information is like totally useless. Like, yeah, maybe some kids are really good at geometry and other kids are like really good at algebra, but maybe that has nothing to do with the actual kind of measures of long-run success and well-being that we actually care about in the education system. Okay, so the current model could still be doing good enough in practice if it's the case that none of that extra signal I showed you over here actually matters for any of the outcomes that we care about over there. Okay, so what we're going to do is leverage some of these modern big data techniques, these machine learning models, to try to use the items and the average measures to ask how well can we explain these long-run outcomes in our data. And then we're going to construct a measure that we're calling information gain, which is basically just saying what share of the predictive power at baseline, how much can we improve on that by incorporating the items into these models instead. Okay, we do it for college attendance first. I'm showing you here for each grade in the data. We do it separately by grade. For college attendance, at least, we're getting anywhere from like a 7 to a 10% boost in performance. Not bad. For high school graduation, on the other hand, we are getting enormous improvements in our ability to detect who is on track to graduate. Anywhere from about 15 to 28% improvement in that outcome. And then finally, for wages, we see a 40%, a little over a 40% improvement in our ability to detect who is going to earn more 5 years after graduating high school. Now, I do want to caution you a little bit on the wage results. These links don't go back nearly as far in time. There was only like one cohort of students where we were able to estimate these models. And as a result, we are not as, our sample sizes aren't as big, but this is at least what you get from the point estimate. Yeah.
So you're comparing like full test information to like one item's information. What happens when you're looking at like the dimensions within the test, right? Like I'm not from Texas, but in Minnesota, we did get like, here's your algebra score, here's your, statistics score. Like how much are you improving in that way?
Great question. So we can do the same exercise using the like official state-aligned categories, and we do basically no better. Okay. And the reason is we've actually done some other exercises where we sort of cluster questions by what students tend to get right and wrong together. And it turns out what the test makers think students are learning does no better than random, or not, it does better than random, not much better than random at predicting what types of questions students are going to get right or wrong together. So it turns out that, just increasing the number of unidimensional measures you extract from the test is not sufficient to get all this extra information. It's really about finding a more nuanced way to harness the patterns in the raw items that are leading to these large information.
Are you gonna tell us anything about the types of items that predict, say, college attendance as opposed to high school graduation?
Can you?
Yeah.
I'm gonna have a slide on this. It's in progress is the short answer. But I can tell you what we're currently doing there, and I would love, especially after this is over, if you have some feedback. Okay. We have a similar exercise where we ask sort of for the extra information that predicts long run outcomes, how much of that is connected to teacher value add as well on the items, and the answer is a lot. So similar finding holds for teachers. And for the sake of time, I'm not going to show you them. Finally, the last thing we want to convince you. So again, we've shown you there's all this extra information over here. The arrows to the outcomes we care about don't run through ability, okay, or the traditional way of aggregating data into ability. They run over here. It is still possible, though, that the decisions we make using average ability are close enough, right? It's incumbent upon me to convince you that actually incorporating this information could lead to different ways, different models of decision making. Okay, so that's what I'm going to try to convince you of now. So what I'm going to show you here, I'm going to take starting with students, and I'm going to predict how likely you are to graduate college using the average test score. That's what's going to be on the x-axis. Then I'm going to predict how likely you are to go to college using the items. Okay, if the current way of making decisions is using all the information, then these two predictions should basically be identical. Okay, they should fall on the 45-degree line and not exhibit a lot of dispersion. That means for any individual student, if you hand me their aggregate score, I'm going to make roughly the same decision I would make as if you handed me predictions with the items. So here's what we see in practice. So two things. So each of these dots is a student embodying those two measures I described earlier. The line is the 45-degree line. Two things about this graph I would like. Oh, and the heat map is telling you kind of a rough visual impression of where there are lots of dots versus less dots. Two things I would like you to take away from this. One, even if I forget about individual students, it's a little hard to see because there's so many dots. We're actually not even getting it right on average. You can see up here at the tail, we're like systematically deviating from the 45-degree line. A prediction we can formally test, and we can reject that you're not even getting it right on average. But I think even more striking is the fact that if you just took any individual student, like this person up here, you know, whether you use the aggregate measure or the item measure, you get a radically different sense of who's doing well. Okay. One way of quantifying the discrepancy at the student level is to ask, you know, what share of agreement is there on who are the lowest performing students? And in general, we have a similar plot over here we've made for teachers, where now we're looking at teacher value added on the predicted values. So that's what's going on over there. One way of quantifying how big the discrepancy is that we find less than 50% agreement regarding which students are highest and lowest performing, depending on whether we use the aggregate score to make our predictions or the raw items, okay? Suggesting that actually incorporating this extra information can really change who we decide is worthy of these extra support and services.
By highest or lowest, you mean like top 10% or?
Yeah. Sorry. This is specifically for the bottom 5%.
Okay.
Which is like the classic Hanashek
Yeah.
thought experiment. We can adjust those thresholds though.
You would expect some disagreement based on measurement error alone, right?
Oh yeah. So we can formally test for the share of agreement where we account for measurement error, and we reject that we reject 100% agreement, which is actually implied by the fact that we also reject it on average. But the short answer is in the paper that we're currently writing that you can't actually see, so it's kind of a cop-out answer. but when the paper comes out, these are just meant to give you visual impressions. We're going to be very careful about how we handle all the measurement error issues. Okay. And then the last thing, I'm going to just go through this quickly because I want to make sure I leave time for discussion at the end. I think I'm already hitting up against the timeline that Jim gave me. But I think this is really cool. I also want to show you that extra signal can influence our understanding of which educational interventions are actually effective. So this is a famous figure. Again, I won't get into the guts of the math. Basically showing the predicted impact, causal effect on test scores of a teacher who is one standard deviation above average in these typical unidimensional metrics, okay? And so then the x-axis tells us how many years after they were assigned this teacher, what is the predicted impact of that teacher on your learning. And the stylized fact that's been replicated over and over, not just for teacher value added, but also for interventions like attending preschool, is that the impact of these interventions fades out dramatically over time, okay? So 4 years after I have a moderately good teacher, the impact of that teacher is predicted to decline by 80%, okay? This has been a puzzle in the literature for a long time. Some explanations that have been offered, like one, it could just be that skills depreciate the same way that capital depreciates. Maybe just like I learn things, I forget, they decay over time, similar to the way like job training programs fade out on wages. A couple other explanations based on like non-cognitive skills. There's a statistical explanation that's also been offered in literature. And I think all three of these things are certainly true and important in some capacity. We're going to offer what we think is a novel explanation based on the observation that test scores are just fundamentally not like wages in the following way. The test you take in 4th grade just is inherently containing different content than the test you take in 5th grade. Let me just illustrate this real quick. Here's an actual 4th grade math item from the tests in our data. It's asking students to find equivalence between a decimal and a fraction. If you go to the 5th grade math test, you find a lot of questions that look like this, where it's asking students to recognize the equation for a line to take an equation for a line and recognize the figure that kind of maps back to that equation. Not obvious to me anyway, that a teacher that improves your ability to answer questions like this is also improving your ability to answer questions like that. Raises the possibility that some of that striking fade out we saw earlier is actually a statistical artifact of the changing composition of the questions across exams. Last ingredient for this explanation, these are the categories I told you about earlier that actually turn out to be really bad. The x-axis is each grade. The blocks here codify the share of the test that the test maker believes falls in each of those categories. And just in practice, if you use these somewhat crude definitions, you see a lot of shifting over time in terms of the types of contents and items being offered. Okay, so what we do here is explore different ways of aggregating the items to see if we can find ways of cutting fade out. And we found one that works, and it's actually very simple. Okay, we're just going to take the 10 hardest items on each exam. We're going to throw away the rest of the test. And we're going to pretend you only took those 10 hardest items defined by the share that students got right and wrong in a given year. We're going to calculate teacher value added on those items and construct this same fade out curve. And when we do that, we can see persistence. Here I'm defining persistence like the opposite of fade out, 0.2. We can double it. Okay, we can double our estimates of the impact of having a highly effective teacher simply by choosing appropriate subsets of the test. Okay, so let me give you some high-level thoughts and takeaways. Everything I've told you so far in this paper has been what I would describe as like pretty destructive. We're trying to highlight the inefficiencies with the ways we currently use the data. Okay, and it suggests that we're throwing away lots of information. We may not be doing as good as we can in terms of research and practice, getting a distorted view of what's going on. And really, we think highlighting some hidden assumptions about how we use test scores, namely that the choice to reduce learning to a single number is sort of equivalent to assuming there's only one dimension of human learning that we haven't spent a lot of time thinking about and talking about. And we think this kind of poses a challenge to the field that we need to do better. Okay, so can we do better? Okay, and we are currently in the process of trying to build something new, but there's some challenges. So for example, items, as I highlighted earlier, are not repeated in the same test year over year. It just makes it really hard if I learn the relationship between the items high school graduation in 2014. Item 1 in that data is not going to be the same thing as item 1 in the next year. I cannot extrapolate backwards in time and use that relationship to predict who in the next cohort is unlikely to graduate. So that's a challenge we're going to need to overcome. I also just don't want to live in a world, right, where I'm like asking high school principals to run machine learning models like every time they want to make a decision, right? What we really need are some form of aggregation, but the right form of aggregation that's actually going to capture all this extra info. And then finally, to be actionable, again, my partner is a kindergarten educator. I'm not going to hand her like predicted high school graduation with that's been like machine learned and value added. We need metrics that are simple and interpretable. So that's where the current agenda is heading. And this gets to Marty's question from earlier. I don't know if it's going to be all of this project or if it's going to go into another paper, but we're just about done with a proof of concept that solves the challenge here by using repeated teacher interactions with the test across grades to link items in a way that allows us to build a small number of measures. And what we find is that we can, for our preliminary tests, we can recover as much as 50% of the lost information using this really simple algorithm. But it's not disclosed, so you're going to have to wait for the paper. Let me just leave you with an analogy. Okay, I want you to imagine you walked into a doctor's office. Okay, and the nurse takes you back to the examination room, and he or she, takes out the tongue depressor. They, put the thing on your back and listen to your heart. They listen to you breathe. They tap your knees, look at your reflexes. They draw some blood, run your cholesterol, shine the light in your ears, and then the nurse takes all that data back to the back room, plugs it into a computer that spits out a number called health that he hands to the doctor. The doctor ignores all the tests, walks into the room and says, Jesse, your health's looking pretty bad this year. We might want to consider surgery. I think we would all agree that's medical malpractice. I would fire my doctor and I'd find a new one. And I think the way we are currently using test score data to make educational decisions is analogous to that situation I described. Now, it's a bit of a straw man. Thankfully, the policymakers are a lot more smart than a lot of us academics. They're doing in-person observations. They're walking around schools. They're looking at qualitative research as a way to discipline the way they're using these test scores to make these decisions. So it's not quite as stark and dramatic. They're using stethoscopes and tongue depressors, okay? But to the extent that their decisions are informed by these unidimensional measures of learning, and they are, okay, we are making this mistake in that step. And the goal of this paper is to highlight that mistake and figure out better ways of using the wealth of data we collect to improve the education system. So hopefully, there's less equations than I'm used to giving in this talk, but hopefully I've convinced you that there is this extra variation at the item level. It does predict who is on track to do well in long run outcomes, and that incorporating it can change the way we make educational decisions. Thank you very much. Question, great.
Thank you, Jesse. I'll open up with a question, but then I'll open it up to everybody else in the room and hopefully online. So there's this tension, I guess, maybe the right word, between, in particular, providing parents with easy to understand information about their child's performance. I think there have been various approaches that different states have taken in terms of how much is too much, should the format be. I think in general, there's a sense that you need to provide some information, but not overwhelm them with information so it means nothing to them. This presentation is focused more around the reporting and use of the data by educators in particular, and school leaders and maybe even policymakers, but not so much parents. So how would you think about what parents ought to be told about their child's performance based on these assessments to give them, on the one hand, something that's simple enough for them to understand, but on the other hand, actually robust enough to be meaningful?
It's a great question, Jim. And I think you are probably 10 steps down the road of where we want to take this research agenda. Let me just start by acknowledging that I actually think, we focus a lot on educators and the way administrators and state level officials kind of use data to make decisions. But I actually think the impact that this data has is maybe even more stark on the parents. Maybe think about it, your end of year standardized test score that comes out. I get these reports from my kids from Rhode Island. That is the only quantitative data I get about my child, other than report cards, which, I don't know how many former educators we have in the room. We all know there's a bit of fuzziness between how they actually do on the exams in the class and the grades that they ultimately wind up with. So if anything, this is probably a more critical area. I think, honestly, we are going to try to reorganize the items in a way that we think is actionable, interpretable. But before I ever wanted to roll something like this out to parents, I would want to do rigorous testing to make sure they understood the measures we're constructing and that they're presented in a way that they can interpret and that will lead to better decisions on their part as well around how to like invest in their kids and provide them extra supports. So that's kind of a cop out because every researcher's, policymakers are always like, what should I do? And researchers are like, we should study it more. But in this case, I think when you're, we view this as really like some basic R&D. I think we were very far from the frontier of being able to put this into practice, but we hope to at some point down.
Great, thank you. Marty, you have a question? Eric? Yep. You go first.
So thanks, Jesse. Still a great paper, getting better all the time.
Thanks, Eric.
I think you're convincing on these points as you've laid them out. My question is like, can you take the educational decision sort of part further? Because so like keying in on the Hanushek bottom 5% example, like we don't talk about it a lot, but it is the case that there's a bunch of noise in the measures anyway. We know that like if you actually did quote fire the bottom 5%, you'd be making a lot of mistakes. So like the fact that you find that who is in the bottom 5% differs depending on the measure you choose, it's not all that surprising because there is this sort of noise in.
I can test that it's not just the noise that's driving the discrepancy. What we don't have is like a confidence interval around that 50% number that adjusts for the noise because it's just hard to do. It's hard to do inference on rank statistics, basically.
That's fair, but either way, it's
fair.
not like we know the truth and we can identify the bottom. So like there's a lot in the paper already. Have you thought about extending some of the Steger, Rockoff, Rothstein sort of richer version of the Hanushek 5% idea to say like, okay, let's see how our decisions would change. And perhaps most importantly, like would we do better on the objective function that we actually care about, which is not information, which is like outcomes for kids?
Also a great question. The short answer is no, we have not done that. We should and could. The slightly longer answer is that I think about the world we live in now just has so much data, not just in education, but in all facets of society that we want to think about what is the right way to act on this information. And so I think about this as like one phase of like a decision pipeline, right? So you have like decisions being made at the end, okay? There's some data feeding into them. We're kind of tinkering with this step, thinking about better ways to organize it there. And then you can go back one step even further and think about now that we have tinkered with how to organize things here, how do you redesign the instrument to work best with the algorithm you've designed there? And so I view all three of these parts as deeply related. I actually think the step that you're on, like if you really put yourself in the head of a policymaker and try to like write down well-formulated decision problems that would like trade costs and benefits and allocate things on the basis of causal effect, my sense is like that's at the frontier of econometrics. Those types of problems are very difficult to solve. And so we are not going to try to innovate in this paper. But I guess that's like a long way of a long cop-out way of saying that I'm also very sympathetic to the view that we want to tinker with that last layer as well. But we're just not going to do it here.
That's complex stuff. I think something simple would be if our set an objective function, which is like improve earnings for kids when they're adults.
Yeah.
Compare using the theta score value added for teachers to dismiss teachers to your preferred wage-based measure.
My understanding is that questions like that, unless you make a lot of assumptions that I'm not sure I would be comfortable making, are extremely difficult. If you want to allocate resources on the basis of causal effects, I think that is a very difficult decision problem. And I played with it actually a little bit in the paper we're writing up right now. We have kind of the stylized framework of decisions. We have like a kind of a welfare function, a policy decision, and an observable that we want to predict. And we want to minimize loss over the welfare function relative to what you would do if you could actually observe the thing you wanted to. And I played around with trying to allow the policy to affect welfare through the observable, and it becomes totally intractable. And I went to my senior econometrics colleagues and asked them, and they said, "Oh yeah, if you figure that one out, we'll give you tenure tomorrow." Well, they didn't quite say that, but so we should talk more offline about exactly what you have in mind. There's other versions of this you could do. that would embed something about, causal effects in there, but not in quite the rich way we had been tinkering.
Jesse, this is a very ambitious and important paper.
Thank you.
So,
I should keep talking to you more often. You guys are great.
so is the
Could be the McKinsey
ultimate
seal.
aim to come up with a better summary measure than the current IRT based ones that we have, or a limited set of summary measures, or is the ultimate aim something different? Because like the second point on its own, just that we can improve our ability to predict graduation, predict college, and predict earnings, doesn't necessarily imply that we can improve our ability to predict all of those with a single summary measure, right? In fact, if I'm interpreting it right, like it looks like our existing measure is, because we don't get as much improvement by going to the item level, best at predicting college and worst at predicting wages, right?
So we get improvements on all three. Can you see the last?
But it's best because the relative improvement
Yeah,
is
yeah,
least for
yeah,
college.
yeah,
So
yeah.
and so we could take Eric's idea and say, oh, let's just set some criteria, maxing out predicting wages. Like, first of all, I'm not sure that would fly in public conversation. But you'd have to go in that direction at some point. One way to think about these current summary measures is they're like a weighted average of our ability to predict multiple different outcomes that we all care about in different ways. And maybe we should be more transparent about that, but like, react.
I agree with you. Could not agree more with everything you just said. Let me tell you a little bit more about this exercise here that we are hoping to have in the paper. We're hoping to release the paper in the next month or two, but probably won't come out for like 2 years because that's the timeline of these things. So one, I think we don't want just a single number. I think we want multiple ways of quantifying the information, the items. And you might imagine, for example, well, let me tell you what it did. Okay. So what we've actually done here is we can see for teachers, like say you have a fourth grade teacher that teaches in 2016, 2017, 2018. I can see in each year the share of students that got item 1 right, the share of students that got item 2 right, the share of students got item 3 right. The intuition behind the simple algorithm is we're going to say, look, if teacher 1 did really well on items, students did really well on items 1, 2, and 3 in this year, and 4, 5, and 6 the next year, it's probably because they're testing the same underlying trait and concept. Okay, so we're clustering on the basis of classroom performance. Okay, this we find that we're doing it with 4 clusters or 5 clusters right now because that's the number of categories the state has. Once we have those, what we're actually doing is redoing every exercise I just showed you, using those as our predictors to see how close can we get to the raw item kind of benchmark that is like infeasible to use in practice. And so what we're finding is that for most of these exercises, we can get like a 50% improvement relative, or we only reduce our ability to predict these things by about half relative to what we could do if we had the raw items. So at the end of the day, what I would do, and then we've also, I have like a spreadsheet in my inbox that I've not looked at closely enough yet that takes each of these clusters and shows us the questions that are in them. So we can try to think about making them actionable, interpretable. If you like, one more thing, the last thing I'll say in terms of like how they can be actionable, interpretable, stylized fact. We actually tried to do this in Massachusetts first, but then they shut the project down. And one of the things we found there is we had the hardest question on the 10th grade high stakes year in math. Like 20% of students get this right. Okay. We predicted that with every other item the kids took that year. And then constructed a measure called feature importance that tells you how much of the variation each of those other individual items can explain. 4 of the top 5 predictors didn't even come from the math test. They came from the ELA test.
Yeah.
And the question turned out to be a word problem.
Yeah.
And so those are the kind of insights we're hoping to get out of this
All right,
reorganization.
so let me go to since I was so polite before, I'll go to my criticism of the paper, which
Please.
I think that last
Criticize.
step starts to address, which is a very atheoretical paper, right? You're just totally going in and letting the data speak in a way that's like uninformed by anything that we know about teaching and learning. And it seems like you could bring some simple hypotheses to it, like just one would involve the difficulty of the item overall and just see, do more difficult items predict college and more easy items predict high school graduation? Like that would be a hypothesis that you could bring to it. And then like, but you could also, it seems that these categories that are generated for you by the test maker aren't very helpful, but you could also think about the extent to which items might be tapping into something that's more like native cognitive ability and something that is more curriculum based and maybe therefore instructionally sensitive. It seems like that would then, if we could start to identify the specific items and the types of items that are predictive of things that we care about, then you could think about how you would shift instruction to move in that direction.
100% agree, and we're hoping that this thing at the end here, we'll be able
Yeah.
to do some of that by offering interpretation. Now that, like, clearly, and we can and should do exactly what you're saying. It's just hard when we found that the categories were not actually picking up a lot of signal, because now I need to impose some other structure on them, and this is kind of our
Yeah,
way
you
of
have to
going-
code items somehow.
Yeah, do you want to hear a really wild idea? You want to hear like some pie in the sky stuff that we're gonna do like years and years from now? Maybe I can tell you afterwards. I don't want to interrupt the
You don't want to give
discussion.
away your best stuff.
Oh,
You're gonna
yeah.
be listening to what's being
Tell us now.
recorded.
Okay, so you guys know like ChatGPT, like large language models?
Yes.
Okay, the way these things work is they reduce like these are already trained by Google on like all of human language. Okay, so we don't have to worry about training it. You can reduce language content, and there's similar stuff for images, into a really large vector of numbers called embeddings. Okay, what we are hoping to do after we complete this proof of concept, we've digitized every test in our data. And so we have the images and the raw text of all these questions, is to reduce all that information down to embeddings and learn the relationship between things like embeddings and long run outcomes. So then you could actually try to like algorithmically redesign the test by finding embeddings that are highly predictive of earnings and using like a ChatGPT like decoder to then reverse engineer what the question was that would give you that embedding. So the short answer is like, all this stuff is on the to-do list, maybe not in quite the way you had been envisioning, but these are all things we are thinking about and working towards. And probably that idea is going to fail because it sounds like too good to be true, right? But that's research. So
Other questions?
yeah,
Yeah, great stuff. I have about 1,000 questions, but I will limit myself to one very short clarification question and one more substantive one. Can you just tell me what type of score you use for the aggregate score? Like what sort of what IRT procedure? And then I have another question.
so we actually just use the average score because the IRT scores do worse.
Really,
The scaled scores and the IRT scores do worse. Yeah.
that is very.
We're being conservative. I mean, the average is like a well-defined thing with like good statistical properties under basically no assumptions. If there's like a single dimensional of learning and the structure of the error term and the IRT model is correct, then you're going to get the right thing at the right aggregator out of that procedure. And so it suggests that, well, I mean, ours, like the first chapter of every IRT graduate textbook I've looked at so far usually starts with like, okay, like this model only makes sense if there is a thing we can all agree is like called math data. And then like, once we agree that's there, this model's great. And to be fair, like this isn't like a crazy way to think about organizing information in the items. You know what I mean? Like the test makers, my understanding, and maybe you can give me even more insight on this, is that it's like they're like these curriculum benchmarks that are developed, and then the rest of the models are being applied to try to like line up with those curriculum benchmarks and boil it down to like a single number. It's the real like pipeline as it's put together, the disconnect between the decisions in the item creation and the modeling stage that I think we're kind of highlighting.
What's surprising me about that though is like that the mean score would assume that every item has equal information, and like getting 20 out of 40 is the same no matter what 20 you get.
It's a bias variance trade-off though, because because you're talking about how to reduce the variance in the measurement error in the average that I pull out. But what I'm saying is that if the IRT model is wrong, that's going to be biased relative to what you would get if you had the true model with the correct number of dimensions and that sort of thing. So I agree with you that the IRT is like very well optimized to like reduce the variance in the measure of student learning. It just turns out that the assumptions you need for that model to also give you something unbiased, we can just show like these actually map to some, these exercises, you can map them to assumptions in these IRT textbooks, and they're basically tests of those assumptions in a lot of ways, and they're just wrong. At least the one that we think is most wrong is trying to reduce it down to a single number. It could be that like a multidimensional IRT model, which I think no one actually uses in practice. Maybe that does great. Like I don't want to sit here and say that all that technology is not not able to capture this stuff. Maybe it would work great, but that's not what they're using in the state of Texas.
Which actually leads into my second question, which is like, how bad is the fit of the unidimensional model? Because we can fit unidimensional models, get fit statistics. Like one thing I would worry about is we would, as researchers, we fit a unidimensional model, go, oh, fit looks okay, let me use these single scores. or let's say like I run a PCA or exploratory factor analysis, like what percent of the total variance in the items is that first component capturing? Because it seems that would be very closely related to the like what percent
Yeah.
of information I might lose.
Yeah, so on that point though, when you do the typical fit test that I've seen in the IRT literature, and again, you should point me to some more because this is, admittedly, I'm an outsider. I've just like worked through Andrew Ho's graduate syllabus and then like read a bunch of graduate textbooks on this at this point. So this is a community that we want to interact with more and make sure we understand and are engaging with in an appropriate way. My understanding of these fit tests though is it's also calibrating the sensitivity parameters. So like imagine you're totally misspecified on theta, but what actually drives a lot of the predicted values is like variation in item difficulty. You could get great model fit with some of these tests in terms of predicting, and actually the tests are designed such that there's a wide dispersion in terms of the average difficulty level of the items. And so I would guess like to the extent that like I'm sure they're doing these fit tests when they're developing the items, they probably look great, but that doesn't really it's not directly informative about whether or not there actually is a single dimension of like learning or skill that's driving performance on the outcome.
Michael, have any questions online?
Yes, there's one from Michelle Barmazel. With the emphasis on the impact of highly effective teachers on students' test outcomes, does that imply that teacher training is a big factor and is a significant lever?
Yeah. I mean, when I think about the body of work on what can actually make a difference in kids' lives and education, I think it is a resounding finding over and over again. I mean, unsurprisingly, given that they're kind of like the frontline soldiers who were like creating skills and human capital in our kids, that teachers are like, I would argue, the critical lever in the education system, which is part of why I think finding better measures of learning to give them like more constructive and targeted feedback is such a critical topic.
So one question I have is whether sort of we're looking at the right thing, meaning the test versus the standards. So, the tests were sort of designed, and I'm not expert in this field here, but as a layman, the tests were basically designed to assess how much students have learned that they were supposed to be taught. Right. So it's sort of and what gets tested each year is mixed up a little bit because they want to try to create some incentives for the whole set of standards to be taught at each grade level rather than just like one or two things. The other thing it measures, I guess, is, how advanced was your learning? So there's some, more complex or hard questions as well as easier ones. They're not really designed to be predictive of college graduation or college matriculation or earnings or anything like that. So in some ways, this seems to beg the question about whether we've got our standards right, so that we're asking teachers to teach the stuff that matters to long-term outcomes, as opposed to whether we're assessing appropriately. Can you just comment on that?
So that's a great question. And so let me try to say it back to you in a really stark way so I can highlight the tension that I think you're getting after, which is like, suppose my algorithm is awesome and I find like the 5 questions that predict, long run outcomes, and they're all about geometry, right? Does that imply that we then want to redesign the entire math curriculum to, well, probably not geometry, this is statistics. I'm gonna be nice to show. It's all about statistics. Does that imply that we want to redesign the entire curriculum to emphasize that? And the short answer is like, well, it's hard to give a short answer to that one. Like, I think I would strongly argue no. Even if we wanted to like optimize on earnings, like I just think there's value to understanding and learning complex topics about the world. I am like very grateful for the education that I've had over the years, even the classes that, did not directly translate into the skills that, Brown is paying me to leverage. And I think we don't want to impoverish our notion of education by reducing it to, just what predicts earnings. That said, whether the current alignment of topics trades off on the tension you've highlighted appropriately, I would want to think about more. And I could imagine emphasizing some things more than others, making thoughtful choices around, given that, I'm not pick on any fields, like some, topic just does not seem to matter for long run outcomes. How much do we want to emphasize that relative to something that really does appear to matter? I think would be the right way to think about it.
But I guess this gets to this idea maybe that the scaled score, the performance categories I'm not saying they're perfect by any means, but that they're actually a pretty fair representation of what you learned, again, based on the standards that define what you were supposed to have learned during that period. And so that's one
Yeah, that may
piece of
not be
information.
true.
Well, right, that may not be true, but that's one
Yeah.
potential. And then there's the other part, which is, but there's more information here, getting to your point, that we're throwing away that actually is predictive or tells us other things that this first measure doesn't tell us. But it doesn't mean the first measure is good, bad, or indifferent. It's just measuring something
Exactly.
different. Okay.
Put very well.
I have a question about your second bullet. So yeah, I get the point that like in general items aren't repeated year over year, but some of them are, like psychometricians embed them for that purpose, right? And I was curious, like, were you able to leverage those items at all to learn anything interesting?
So they won't give them to us. They're like top secret because they're afraid if you know the items that are repeated year over year.
Oh, so you can't see them.
If I had the anchor items, I wouldn't need to do all this like crazy clustering, you know what I mean? And then I could just directly, like, so, like the problem, like, once I have one item that's like, I know for sure is like repeated within the same grade across years, then I can benchmark everything in both tests to performance on that item. So then it's like, I'd have to think about exactly how we'd want to do the clustering exercise if we had those, but we don't have. So we're in a,
So you actually can't go through and code up the items based on their characteristics.
no, I see the test, but they don't release the anchor item.
Oh, okay.
I don't know if I'm using the correct.
I see the items that are repeated across grades.
Yeah, those are
or
like,
across years.
those like, you'd think I was trying to like break into, like, steal the nuclear codes or something.
Yes.
Michael, any more questions online?
I'm sure you've thought about this, but, this definitely puts me in mind of like Bo Jackson's paper about like different kinds of teacher contributions and whether those predict different long run outcomes. And like, I feel like some people felt like the sky was falling when they read that paper too, like, oh, test score value added doesn't predict high school graduation, like maybe we shouldn't care about it anymore. These sorts of thoughts. I don't know if you've seen, Dan Goldhaber and co-authors have a new paper where they repeat some of those methods.
From Bo Jackson's paper?
Yeah.
I'm not familiar with
Same
it.
value added measures, but they have a larger set of outcomes beyond just like high school graduation. They look at going to college, going to an elite college, wages. And it turns out that the value added measures are predictive, but the test score value added measures are predictive of like going to an elite college. Both measures are predictive of wages. So it seems like there are some parallels here, right? That we're missing. We have that's a sort of a more blunt or at least a different way into the same problem of teachers are a vector of skills and capacities. Maybe some teachers are better at X or Y.
Yeah, no, the way I've not read the paper, but the way I could try to build the bridge there is if they're showing how well it's doing with teacher value added on the average,
Right.
imagine how well we could do
Right.
if you let me rebuild it from the ground up using the items, and imagine how much better we could do if you then let me rebuild it from the ground up, redesigning the test.
Yeah, so I guess one concrete question would be like, again, you have way too much, and you probably have too much in the paper already, but like, take your, just using the test items for like high school students to predict graduation, going to college, et cetera. That's sort of approach one. Approach two is use things that Bo used, go into, like grades, attendance, discipline, like what happens in that horse race.
Yeah, we could absolutely do some of those. One place we don't see a lot of gains is on the average score. Unsurprisingly, given how the test is kind of like optimized or to align with the IRT data type model. But we've not done things like attendance and we could. We just pick these ones. One thing I will say though, Evan Rose and Yotam have a paper also doing Bo Jackson's exercise, but in North Carolina. And my memory in their work is they're looking about interactions with the criminal justice system. And they actually find that value add does not do a good job capturing teachers who are effective at reducing criminal justice content. So I guess it's like, highly context dependent.
All of these papers, I think, are in Carolina. Bo's paper.
Oh, is it? Is it? Yeah, it's been, I thought Bo's paper was in Chicago for some reason. And then I would have assumed with Dan, it would be like Washington State, right? But yeah, so.
Teacher one is North Carolina.
But yeah, no, it's a fair point. We absolutely could. We could benchmark these exercises to some of the other like average value added type, but non-test score outcomes that have been said. The one thing about all those things, it's always lurking in the back of my head, and I don't know, maybe you have thoughts on this, Eric. I'd love to hear them. Is like if you go into like the guts of the Chetty Freeman and Rockoff paper, like I'm pretty sure like value added models are biased for the causal effect on long run outcomes, right? Like that's in the appendix. It's like I'm not really sure. I get that like once you have a value added measure, you can just try to predict long run outcomes with it. What we really want is the causal effect on it.
Jim Solon gave a talk here a few weeks ago, and I asked a similar question of him. And I'm curious, have you tried just going fully latent variable approach for your predictor and saying, instead of even trying to score the test, let me just
Like PCA and
not PCA, but like more like structural equation modeling. Like let me actually simultaneously estimate this measurement model and use that as a predictor. Because that seems like to me it would theoretically capture the maximum information in the individual items.
No, that's a great, actually, one of the papers that inspired me most in grad school is this paper by Jim Heckman and Flavio Cunha and Susan Shinak, where they basically, it's probably not exactly what you have in mind. They're gonna develop a latent factor model that's meant to embed things like parental and school investment. And so it's a little more structural in the econ sense of kind of modeling like decisions about the world, but it does embed this latent factor structure. And then they're gonna link that to long run outcomes in the NLSY data. So they do something very similar to what you have in mind. We have not tried to do that here. We could. I'm a little worried though, like, well, no, we could try to do.
Because it would be easy to have that item, so it'd be very easy.
Yeah, because we have
And then you
multiple
can
measures of, yeah.
simultaneously estimate the IRT model
No, we could.
and the predictors, and that would theoretically disattenuate the predict, because their
Yeah.
predictors are attenuated anyway. And it doesn't matter what way you score the test, that's gonna happen. So I'd be very curious if that's, and then you could in fact get a parametric test of, so you could fit the structural equation model. And then you could add a different additional paths from each item to the outcome and then test those as well. And then you get like, oh, here's a p-value on, is this item giving me more information above and beyond this like that?
Yeah, you're right.
Low hanging fruit.
No, we absolutely could do that. I think, we approach this, so like the trade-off in my view on any of these more structural approaches is they're gonna require more assumptions, but like, that's statistics. We're in the business of compromising with the data. And I think our prior going into this project, given the existing state of how people are using and thinking about processing the information in tests, was to go to the complete opposite of the spectrum, where we just want to leverage the fact that we bought the state of Texas like a new server to handle these out. Like these are not, you can't run these on your laptop, you know what I mean? And so we've in some ways gone to the other extreme, but you're right, like we could benchmark relative to something that does it in this framework, and we've not.
I'll pose one last question about a word you used twice early on in the presentation. You were saying we increasingly use test scores to make high stakes decisions. And I want to know, do you really believe that? Because it seems like there's been a significant rollback on a number of dimensions over the past 5 to 10 years. And maybe it's a long-term claim.
Yeah, it depends on your reference.
Yeah.
No, you're right. Probably in the last 5, 10 years. Like another way you could think about framing this is like there's like this wave of innovation in developing this infrastructure for state level standardized testing in like the 90s and early 2000s, like culminating in No Child Left Behind. And now everyone is like sick of it. Parents are mad. My partner, she's mad. She doesn't like getting, she feels constantly under stress about the districts, the way they view data. And so one way you could frame this is like, instead of saying increasingly rely, is that we're in the
Why are
backline.
people frustrated with it?
Why are people frustrated?
And how could we
Can
do a better job?
I totally agree.
All right. With that, Jesse, thank you very much.
Thank you so much. I really appreciate all your questions. It's been super fun. Thank you.
We'll be back next week. See everybody.
Right?
Then-
I like that.